In this section, we begin our study of a very important example of a kind of series called power series. So let's start with the definition. The basic idea here is that a power series is going to be the infinite analog of a polynomial. And as we know from our study of calculus, polynomials are the nicest kind of functions you can ever dream of in a calculus sense. So here's our definition of a power series. Let's suppose that we have a sequence. So suppose, let's say, we'll call these C sub n. These are a sequence of real numbers. All right. And let's also suppose that x naught is some fixed real number. So x sub 0 is some fixed real number. Then a power series, or then the corresponding power series given this information, is the function given by the following formula. So the corresponding power series with coefficients C sub n. So the coefficients here are the C sub n's, and center x naught, so x sub 0. So the coefficients are the C sub n's, the center is x naught. This is the function with the following form. So I'll call it P of x because it's called a power series. So P of x is our function, and it is given by the infinite sum, or the series, as n goes from 0 to infinity, of C sub n times x minus x naught to the power n. Okay, so in this scenario, the x is a variable. It's allowed to change. The C sub n's are constants, but they're different for every n, potentially. They're allowed to be different for every n. They come from this sequence up here that we started with. So the sequence of coefficients. And then the x naught, this is called the center of the power series. All right, let's write out the first few terms, and you'll see why my original comment was that these are the analogs of polynomials. So this is the end of our definition. Let me draw a little line here, kind of differentiate. But there's our definition. Let's write down the first few terms of a power series with this coefficient series. Everything is symbolic right now, but our P of x is going to be, when n is equal to 0, it's going to be whatever the first term of the sequence is times 1, right? So anything to the 0 power is 1. So this is just going to be the constant term, plus the next term, when n is equal to 1, we get the next coefficient, C1, plus the term where we have x minus x naught to the power 1. So that's just the linear term. And then the next term is going to be, we see how this is going to go, C2 times x minus x naught squared, plus the next term, C3, x minus x naught cubed, and on and on. Eventually we get to the general term, Cn, x minus x naught to the power n, but then it continues on forever. Okay? When I say forever, I mean, you know, these continue on. This is a series, right? It continues on as n approaches infinity. And notice that if we were to cut this off, say right here at step n, and just keep what happens before we cut it off, then this is obviously a partial sum. Okay, so the partial sums of these power series are just polynomials. So now this is truly a polynomial of degree n. Okay, so I'll call this a fact as far as our notes are concerned, but the partial sums of our power series, so the partial sums, these are called, say, let's call them P sub k. These are still functions, right? P sub k of x of our power series, P of x. These are polynomials whose degree is up to k. It's possible that some of these coefficients could be zeros, right? But these are polynomials, right? Polynomials of degree up to, or at most, k. All right, so again, the partial sums are P sub k of x equals the first term, C naught, plus C1, x minus x naught, plus all the way up to, eventually, C sub k, x minus x naught to the power k. All right. Again, it's possible that the C sub k is 0, in which case the degree of this polynomial will be less than k, but it can't be more than k. So at this point, we've made a restriction that the degree of the partial sum, the degree of the polynomial, which we're regarding as a partial sum, is at most k. All right. And so that means, what that means then, and as always, right, we can always think of our power series, any kind of series, right, the sum of a series. Our power series is then, if we want to think of this in the sense of a series itself, the power series function is a limit as k goes to infinity of these partial sums p sub k of x. And what we have to do is we have to interpret this piecewise, or pointwise, excuse me. So in other words, we have to interpret this in our mind that we have chosen a value of x, we have fixed it, okay, and then we have taken a limit of the values of the corresponding kth degree polynomials, right? And so it's possible that for any given value of x, right, this could be convergent for some x. In other words, this polynomial could make sense, right? So this value could be convergent. We could get a value, right, for certain x values, for certain values of x, but it's also possible that it could be divergent for other values, right? So for other values of x. And therefore, it's going to be a big question for us to have to answer that given a power series, for what values of x is that power series convergent? And obviously, for what values is it divergent? The question of when it's convergent is more likely. It's more likely that we're going to want to know the answer to that one, because convergent means that we actually get a number back. And so in that case, in the case that the power series is convergent, then we can think of the set of all the values of x for which the power series is convergent as the domain of the power series. Okay, so we'll write this as a definition. But given a power series, p of x equals the sum, n goes from 0 to infinity, c sub n coefficients, x minus x naught to the power n. There's the power series, the thing that makes it a power series. So given this power series, the set of all x values, all right, for which this series converges, so for which p of x converges, this is the domain of the power series. So it's called the domain, and this is just in the idea, in the function theoretical sense, the set of all values for which when you plug the value in, you get an answer back. That's the domain of a function, right? And so this is the same exact idea, except get an answer back means that the series must converge, right? If the series doesn't converge, we don't get an answer back. We can't make sense of that. So again, I've gotten myself off track here, but the set of all x values for which the p of x, the series, converges is called the domain of the power series. So that's how we're defining this. All right. Now it turns out that the domain of a power series always has a really nice form. So there's a theorem about this later in the notes, but I want to write this down now. So that's the end of our definition, right? But the domain of a power series, I'll abbreviate P dot S dot, power series P of x equals sum, n from 0 to infinity, c sub n, x minus x naught to the power n. This domain has a very nice form, okay? And I'm going to just keep saying nice. I mean, you'll see exactly what I mean by this word nice in a few moments, right? So here's the idea. I want to know, does this series converge, okay? Or for what values of x does this series converge? And so I can apply, or try to apply at least, the ratio test to p. All right, and if I do this, remember the ratio test says the following. We want to look at the ratio of these terms. So this is like the a sub n of my power series. If I fixed an x value, this becomes my a sub n of a series, just a regular series, right? So the ratio test says I should look at the ratio of a sub n plus 1 over a sub n, and then ask what happens as n approaches infinity. Right? So what happens to this as n approaches infinity? And we have some rules about this. We know that if this limit here converges to a limit that is less than 1, then our series converges. If it converges to some limit that is greater than 1 or infinity, right? If it diverges to infinity, then our series itself diverges, right? And if L equals 1, well, That's a question, right? So let's apply this idea to our power series and see what happens. For us, a sub n plus 1 is just the coefficient c sub n plus 1 times the power here, x minus x naught to the power n plus 1. And our a sub n term of this series is c sub n times x minus x naught to the power n. And we want to take the ratio of the absolute values of these things, right? And so I'm just going to draw a little squiggle here. But our ratio test, when applied, is going to look like the following. I'm going to break this up into two parts, okay? I already stacked this up so it looks like a fraction. The c sub n's, the coefficients, these are numbers. So I'm going to write this as c sub n plus 1 over c sub n, absolute value. So we can treat that part separately, but then this entire thing is multiplied by this ratio of x minus x naught over to the power n plus 1 over x minus x naught to the power n. And we're going to take a limit of this, right? So when we take the limit, these terms, the nth powers of these terms can cancel, and what we're left with is just x minus x naught, absolute value. Okay? And at this point, we can see that for any fixed value of x, right, this term is going to be a constant. X naught is already a constant, and if we fix our x value, this is a constant. So in other words, n is not playing any role here, and the limit as n goes to infinity only actually works on this ratio of the coefficient sequence. Okay? And so as n approaches infinity, let's suppose that this portion right here converges to some. So as n approaches infinity, let's say that this right here approaches some constant L. All right, so some constant L, and then we still have this term, absolute value of x minus x naught. All right, now this L right here is not the same as the L that I've written in green when I've restated the ratio test. This number L, this is the limit of just the coefficient, the ratio test essentially applied to the coefficient sequence, not to the power series itself. But what we know though is that if we want our power series to be convergent, right, for a certain value of x, if we want to be sure that this converges, then we need this entire term to be less than 1, right? We need this to be less than 1. By the way, L cannot be negative because we've taken absolute value here, right? And so what we end up with then is that provided this limit L exists, okay, provided L exists and L is greater than 0, okay, then our power series will converge. So P of x converges for all x that satisfy this inequality, that the absolute value of x minus x naught, remember x naught is fixed, right? That's the center, has to be less than this ratio 1 over L. And we've assumed L is greater than 0, right? And we're going to call this ratio 1 over L, this is equal to R. Okay, just so that we have, we're going to be able to compute this, and this will just be a number. We'll call this number R. And this number R, so this R is the radius of convergence of our power series. So it's the radius of convergence of this power series function P of x. Okay, and notice that this tells us about the domain of our power series. It tells us that the power series converges whenever x is within r units of x naught. Okay, so the domain of P is then, I'm going to put in parentheses, at least this, x minus x naught less than r. And of course this can be rearranged to be written as x naught minus r less than x naught plus r. Okay, and so there's an interval. So this is the nice form that I was talking about the domain of our power series. It's always an interval that's centered around this point x naught. And that's why our point x naught is called the center of our power series. Okay, but this is called the radius of convergence. Now, there's a couple questions, and we're going to address these moving forward. This is supposed to be an introduction video, so I don't want to go too much longer. But a couple of questions that you might have is, number one, what happens if L is equal to 0? If L is equal to 0, then actually this number will always be less than 1, right? No matter what. for x naught, x minus x naught. It'll always be 0. 0 times anything is 0. So if L is 0, then we say that our radius of convergence is infinity. So if L equals 0, the radius is equal to plus infinity. And that means that the domain of the function, all right, the domain of the function is equal to all real numbers. So it's the entire real number line. Okay? The other question is, what if this limit does not exist? So the limit of the c sub n's does not exist, but it does so in such a way that this limit is equal to plus infinity, right? So if L equals plus infinity, in that case, honestly, if it doesn't exist in any way really, then it's going to be impossible for us to find any x values for which this equation right here is satisfied. All right? And as we get deeper into the notes, we'll see that our series, our power series, always converges when x equals x naught. Maybe you can pause and think that through right now, why that would be true. But it turns out that that is true, that our power series always converges when x equals x naught. And so if L equals infinity, or even if it just doesn't exist for some other reason, then we say that R is equal to 0, and the domain of our power series function P is equal to simply that one point x naught. Okay? And so it's actually not really much of a function at all, because there's only one point in its domain, and if you try to leave that point at all, try to vary even the tiniest bit in either direction, your series will diverge. Okay? So one last thing that I want to say before I end this lecture, and I know it's getting a little long here, but the one last thing that I'd like to say is, if we know that our radius of convergence is R, then we learn that we have this domain, right? The domain looks like this: x naught minus R to x naught plus R. This is called our interval of convergence, but it's not exactly the whole story. Okay, so the interval of convergence of a power series, the interval of convergence of a power series P of x, all right, it's this interval. Obviously, it's called the interval of convergence, so it's an interval, and I'll just write it in absolute value notation, but it's x minus x naught less than R with a couple of caveats, okay? So it could be, again, let me just write it as minus R less than x minus x naught less than R, okay? So this is another way to write the same thing, but here's the caveat. The ratio test that we used to get this interval, the ratio test is inconclusive when L equals 1. And remember, this L is not the same as this L. So it's inconclusive when the thing in the orange box here equals to 1. And if it's inconclusive, that means we need to do more work, right? And what could happen? Well, these points are already removed from our interval the way I've written it here. So it's possible that in our interval of convergence, we might actually want to include these values that correspond to the endpoints of the interval. Okay? And so the interval of convergence could be totally open, it could be half open on either side, or it could be totally closed, meaning that both endpoints are included. So no endpoints, one of the two endpoints, or both endpoints.